Hello all, welcome to this webinar where we are going to discuss about power estimation models for edge computing devices. So the edge computing is a new paradigm of processing where data and running applications are closer to the edge of the network and nearer to the data source. Due to the increasing adoption of edge computing, the proliferation of Internet of Things devices led to an increasing demand to handle massive amounts of data generated at the edge. And therefore, the energy estimation for these devices is crucial for optimizing resource allocation, improving system performance, and ensuring the sustainability of edge computing devices. However, the heterogeneous characteristics of edge computing devices pose a challenge for creating a unique power model for all the devices. And therefore, we present a methodology for developing power models that are tailored to the computing devices. So on this slide, you can see the methodology that we follow for this work, which is composed by 5 different modules, and which we are going to analyze further in the next slides. Over here, you can see the workflow and the data flow between each of the modules. So starting with the data monitoring and storage module, a monitoring agent is deployed on the device under test and is responsible for constantly collecting the resource utilization and the power consumption metrics on real time. This monitoring agent is a lightweight process with minimal resources utilization in order to avoid interfering with the collected data and put some noise in them. The monitoring agent is also responsible to communicate those results to the storage agent that is deployed to a remote device at predetermined time intervals. And the storage agent is a time series database which we can use to collect the results using the respective timestamps. For CPU utilization, we make use of the percentage of the utilization that is used. And for network subcomponents, we make use of the metric of kilobits sent or received per second. The device benchmarking module allows users to measure and compare the power consumption of different device components upon request, such as CPU and network at their different utilization levels. Users can select which subcomponents to include in the models. For CPU benchmarking, we typically make use of the stress command provided by the Linux distribution. And for network subcomponents, we make use of the iPerf command in order to stress network modules at different rates on client and server roles. The relevant timestamps are recorded for the period of time each benchmark is executed. And we can use any form of workload in order to stress our modules. So our methodology is agnostic to the workloads that we make use for stressing those subcomponents. For data collection, cleaning, and pre-processing, so as we already mentioned, the relevant data and for resource utilization, power consumption are retrieved from the storage agent based on the recorded timestamps. And due to the way that we monitor those devices, there is a number of outliers that may exist in the data set. And typically we consider as outliers points that are further than 2 or 3 times than the mean in the distribution of power and resource utilization. Also, since some components are related between each other, like CPU and network, in order to accurately calculate the power consumption that is relevant to each component, then we make use of the power consumption that is calculated for the CPU in order to calculate the rest. In the models training and evaluation module, the users can choose to create additive power models that are consisted by multiple polynomial models for each subcomponent. For example, here you can see a typical example where an additive model is created for our system that considers the power for CPU network and the idle power consumption. Also, the users can choose to create regression or ensemble models that take as input all the utilization metrics that the user has chosen. Our methodology is agnostic to ML and mathematical models, and it allows users to leverage different libraries and models based on their preferences and their requirements. Also, the users can select to auto-tune the hyperparameters of the selected models in order to optimize their performance. At last, the evaluation is performed based on some performance indicators like mean square error and mean average percentage error in order to choose the most accurate power models. Further to that, our methodology provides users the ability to test their models on real world applications once they are generated. Also, our methodology provides the flexibility to use any sort of workloads for the evaluation of the generated models. So for our scenario, we chose to make use of the MLPerf image classification and detection workload that is a real-world application performing inference on a set of images. And because we chose to use the Raspberry Pi 4 as our device under test, we make the necessary adjustments to the Docker image in order to make it compatible with the ARM architecture of the Raspberry Pi 4. The same methodology for monitoring and collecting the results was followed in this case for the period of time our workload was executed. We also made the necessary adjustments to the underlying code of the MLPerf inference workload in order to support inference over the network. So the reason that we chose Raspberry Pi 4, as we already mentioned, is that it's considered as an edge device that can be used by a variety of edge applications, including machine learning applications. The device under test exhibits a gigabit Ethernet interface with a maximum bandwidth of 1 gigabit per second and an integrated dual-channel wireless antenna and 2.4 and 5 gigahertz accordingly. We also made use of Hemero's smart plug in order to record the power consumption of the device under test on real time. So over here, you can see the distribution of CPU utilization versus the relevant power consumption for Raspberry Pi 4. As you can see, the relationship is linear, and the relevant model is written on the bottom of this slide. And on these diagrams, you can see the network utilization versus power consumption distribution. As you can see in the cases of Ethernet download and Ethernet upload, in both cases, the most efficient power models were the degree 3 power models. While for Wi-Fi upload, the model with the least error was the degree 2 polynomial. In the case of Wi-Fi download, we were not able to accurately capture any form of relationship due to the amount of packet losses that were occurring. Some plots for the evaluation results when we ran our workload for performing inference over the network for the images. We chose to use 3 different types of models: a random forest and a linear regression model that take as input the metrics for the resource utilization of CPU and network components, and an additive model that makes use of the individual submodels that we mentioned in the previous slides. As you can see here, in the case of Wi-Fi, the additive model exhibited the least error, while in the case of Ethernet, the linear regression model was slightly more accurate than the additive model. And in this plot, you can see the predicted vs actual power consumption when performing inference on the device locally. In this case, additive and linear models were the same, since we only made use of CPU in this case, and there was no network utilization. And as you can see, it's clear that they perform much better than the random forest. And this may be due to the complexity of random forest that makes it hard to capture these kind of relationships in this case. Some conclusions and future work. This work presented a methodology for generating and evaluating power consumption models for edge devices with multiple subcomponents. Our methodology can generate both additive, polynomial, and some regression models. And our methodology can be useful for creating and evaluating power models for a wide range of edge devices. Future work includes extending our methodology to incorporate information about cellular communication and automating the pipeline of the proposed methodology. Thank you for your attention. I hope you enjoyed this webinar session.